Today, I'll talk about the effects of deep brain stimulation on sleep in patients with major depressive disorder, but also a little bit more broadly about why we might want to start thinking about sleep and circadian rhythms when designing deep brain stimulation systems and deep brain stimulation therapies. So I'm going to start with a few disclosures and disclaimers. So I've previously received speaker fees from Medtronic, and I work in the lab led by Tim Dennison, who has worked in the field for a long time, so he's got a lot of relationships. But the most relevant one at the moment is that he's the co-founder and director of our industry partner, Bioinduction and Amber Therapeutics. And I should also add that the devices that I'll be talking about today are generally for research use only, so they're not yet sort of CE marked for broader clinical use. And I also should add some acknowledgements. So we work, we've got a core team at the Brain Network Dynamics Unit and the IBME in Oxford. We work with a number of clinical teams to do our own clinical trials. And then we've got a number of data analysis projects from clinical teams across the world. And specifically today, the key collaboration is one with Georgia Tech and Mount Sinai Hospital in New York, who've done the depression clinical work. So I'll give you a brief introduction of deep brain stimulation in the context of sleep and circadian rhythms. And then I'll go into the meat of the study on deep brain stimulation, depression, and sleep. And then finally, I'll talk a bit about the progress that our lab is making on a deep brain stimulation system that is designed to adapt or to work with our sleep-wake cycles, our circadian rhythms, in order to optimize therapy. So to start with, why should we care about sleep and circadian rhythms in deep brain stimulation? So if you are not very familiar with the field of deep brain stimulation, the idea is that you've got essentially a pacemaker for the brain. So what you try and do is you find a dysfunctional brain network. So maybe in Parkinson's disease, you know where something goes wrong. You implant electrodes that provide electrical stimulation to try and steer this area back to some kind of healthy state. And at the moment, this is used for symptom control in Parkinson's disease and movement disorders, in epilepsy, in chronic pain, and it's also being trialed in some psychiatric conditions such as depression. And just to give you an idea of what that actually looks like in Parkinson's disease, where it's the longest established, on the left here, you see a patient who has been implanted with a deep brain stimulation system, but the stimulation is off. And you can see that he's got a lot of typical Parkinsonian Parkinsonian symptoms. So his movements are very slow, very difficult. He's actually being assisted down the hallway by these two clinicians or researchers trying to move around. He's actually got real difficulty initiating movements as well. And these are some of the most obvious and debilitating symptoms of Parkinson's disease. The gentleman, or the video on the right shows the same gentleman, but his deep brain stimulator has been switched on. As you can see, actually, the act of turning around is particularly difficult for this patient. So I'm going to skip a little bit ahead in this video to the point at which you see the equivalent video for the same patient in whom the stimulation has been turned on. And I don't think that you or I would be able to actually pick out this patient on the street as having a movement disorder. So it can be extremely effective. And so in practice, how is this sort of therapy applied? Generally, a clinician will set stimulation parameters during a clinical visit, will tweak the stimulation parameters, so in terms of the amplitude, in terms of the stimulation frequency, until some kind of symptom control is achieved, but also trying to avoid side effects that can be common through deep brain stimulation. There is a feedback loop where, obviously this will eventually have some long-term physiological effect. If this changes, the patient might report this. They'll contact the clinician. They'll try and schedule another visit. And so if their response at any point changes, they've got this way of adjusting therapy to optimize it, over a fairly long time scale. And as you can imagine, this is maybe quite inefficient, and also it has a very long time delay, so it won't actually deal with fluctuations in therapy needs on much shorter timescales, say hours. And so what's currently the kind of state of the art and being trialed in a few different contexts is closed loop therapy, where basically you adapt or react to changes in patient needs, and you only stimulate as and when required. But once you start closing the loop, you've created a physiological closed loop control system, and you're going to enter into the realm of control engineering. And so what you need is, first of all, you need some kind of biomarker. You need something that correlates with your disease symptoms so that you know how much stimulation is required. The second thing you need is you need to know where you want that biomarker to go. So in the case of Parkinson's, for instance, there's a well-known biomarker, which is a type of electrical oscillation in the brain at a frequency that people call beta. And generally, when that is high, patient symptoms are high. And by providing electrical stimulation, you reduce the amount of beta and you reduce the symptoms. But finally, you also need to have some kind of understanding of what your stimulation is going to do to that biomarker. So as you increase stimulation, are you going to increase or decrease that target activity? And I'm personally a neuroscientist by training, so my job title is neuroengineer, but that's kind of a cheats title because I didn't do an engineering degree. But hanging out with engineers is very informative, and you learn some interesting things, like the good regulator theorem. So this is a paper from the early days of, or from actually the heyday probably of cybernetics and control theory. And it states that every regulator of a system, every good regulator of a system must be or must contain a model of that system. And what does that mean? So I've told you that we need to know about biomarkers, but we also need to have some idea of the dynamics of that biomarker. We need to know what our stimulation, we need to have some idea of what changing our stimulation parameters is going to do to that biomarker. And so really, are deep brain stimulation systems good regulators according to this principle? And really the question to ask then is, what do they imply about the dynamics of the brain? And a lot of these therapies were developed during the daytime, during clinical research visits, where people measured beta from externalized leads. So the deep brain stimulation system contacts were implanted, but not yet connected to the stimulator, so people could record the brain activity from the deep brain stimulation target. And there, people have acquired knowledge about the dynamics of beta and how it responds to the stimulation, but you miss some things on much longer timescales. And so one thing that we know is that human physiology is actually not static across the diurnal cycle. I've taken the liberty here of putting the Vitruvian Man through his circadian paces using Midjourney, because it seems to be obligatory that every circadian graphic has a Vitruvian Man. So here's a Vitruvian Man doing some architecture in the morning, because that's when we generally hit our sort of peak cognitive performance. Later in the day, it's time to do some Renaissance sports, because we hit our peak physical performance sort of late afternoonish. In the evening, while we might want to be sort of drinking and feasting, actually our body wants to be winding down to prepare for good sleep. And then at night, we sleep. This is a very important activity for a lot of physiological and cognitive processes. In order to achieve this, our body needs to be in the right state for that. And so ultimately, this is a predictive system that is getting our physiology ready for the expected state of the world. Now, I don't expect that anybody flew in for this meeting, but if anybody happens to be jet lagged, then you probably know what it means to be to feel profoundly out of time, for your body clock to be out of sync with where it needs to be. And another sort of long-term change in brain dynamics is not just circadian, but is kind of a transition in states. So if we put some electrodes, some EEG electrodes on the Vitruvian man's head while he's awake, we might see something like this. Waking activity is fast, relatively low amplitude, like ripples in a pond. But if we look at sleeping activity, we see these much larger amplitude, relatively slower activities that occur. And so going back to the Martian scientist that Chomsky was imagining, as a Martian scientist, just looking at the overall activity of the brain over day and night, you might well infer that the most important thing that brains undergo during the day is the sleep-wake transition. And so really, the system that you're interacting with a deep brain stimulator is doing something radically different between these states. A biomarker that you've characterized during the daytime may not actually behave the way you expect it to at night. And finally, deep brain stimulation itself has the potential to affect sleep or alertness levels. And so this really is a key challenge for the next generation of deep brain stimulation systems. So here's just an example from an earlier paper about the behavior of the biomarker that is used for Parkinson's disease. So I've told you that these electrical oscillations in the brain in this beta frequency range correlate with symptoms and are therefore considered a biomarker for closed loop therapy for Parkinson's disease. Now, if you record them over long time periods, which you can do with some of the more modern deep brain stimulation devices, what you see is this very pronounced oscillation. And it won't surprise anyone in this room, after all that I've told you, that the gray boxes over there are the periods that the patient reported being asleep. So what you can see is that during the daytime, beta has quite a high variance, but it's also quite high. And during the nighttime, it really reduces a lot. So for a closed loop system that's going to respond to beta as a biomarker, it's going to turn down that stimulation during sleep because it assumes that it's not required. As it turns out, even these low levels of beta activity during the night are a real driver of the sleep disturbances that Parkinson's patients experience, and that are actually one of the more subjectively distressing symptoms, because struggling to get a good night's sleep basically makes essentially everything worse. You know, your symptoms, your mood, and so it's a real source of the disease burden. So essentially, trying to use a sort of one size or a daytime fits all approach may not really be appropriate when you send people home with these closed loop therapies to run 24/7. Another point to make about deep brain stimulation in terms of going, so that was an implication of sleep for deep brain stimulation systems, but implications of deep brain stimulation for sleep are that we're interacting with this very complex system here. So in the brain, we've got a master clock, the suprachiasmatic nucleus, which essentially keeps time for us. So even if you put us in the dark for a number of days, or actually basically indefinitely, that system will still generate a circadian rhythm. It will slowly drift ever so slightly off with, the outside world. And that system then drives our autonomic nervous system, it drives hormones, it drives our body temperature, which in turn tell us when we're going to feel sleepy or awake. It tells us when we are going to be hungry. But what's interesting, or what's great about this system, especially if you're ever jet lagged or in a dark place, or spend some time in a dark place, is that perception of light in the environment is a cue into the system that allows that system to entrain to wherever you are, or to the kind of light cycle to the day and night in, say, your time zone. And so that's what keeps this clock in sync with the world as days, weeks, months pass. what's really interesting is that once you sort of start, that your actual behavior also feeds back into the system. So if you consistently stay up very late, even though your environment is has a light cycle that is earlier than your bedtime, or if you consistently eat at very late or early times, that's going to feed back into this master clock and also shift your rhythm. So this is a very, very carefully controlled system. There's a master clock in the brain, and obviously, we stick a big electrode in the brain. Generally, the targets for deep brain stimulation are either subcortical targets that tend to have very strong connections to the hypothalamus that has the suprachiasmatic nucleus, or that interface with important autonomic nervous system hubs that have these strong influences on, hormones or temperature or any of these things. So really, we want to know what we're doing when we're, letting one of these systems run in a patient. And so that's what the next part of this talk will be about in one particular study. So we'll look at deep brain stimulation for depression and how that impacted the sleep of a cohort of patients. So major depressive disorder is a bit of a new frontier for DBS. It's not currently in regular clinical use. But stimulation of the subcallosal cingulate gyrus is an experimental therapy. It's a system that's strongly interlinked with a large mood network, which is why it's hypothesized to be able to help here. And a recent study tried to essentially identify a biomarker. So, as I said before, if you want to have a system that is going to be able to adapt to a patient's needs, that system needs to be able to measure something about brain activity that will help it adjust its therapy accordingly. And so this paper was very exciting because using an explainable AI approach, the team led by Shankar was able to actually find evidence for a potential biomarker. It was quite complex with a lot of different features of neural activity sort of incorporated in it. But it's an important first step for trying to create such a closed loop therapy for depression. And we were very lucky to work with them to analyze the data that they had collected to see what we could find out about how deep brain stimulation impacted sleep. So sleep and depression have a bidirectional relationship. So it means that sleep problems are really an important symptom of depression. But on the other hand, that actually sleep problems have impacts your mood and can actually predict poorer treatment outcomes, can predict relapses. And so there's this very important kind of almost cyclical problem. If you're naturally a late sleeper and a late waker, that tends to, that is a risk factor for depression as well. And in depression, sleep structure tends to be altered. In particular, non-REM sleep, the sort of deepest sleep that we get, tends to be delayed in depression patients. And you might even see earlier REM sleep, so the type of sleep that is usually associated with dreaming. And so for this project, we worked with these patients from this trial that was conducted at Mount Sinai Hospital. And they were implanted with a particular deep brain stimulation device that was actually able to take some snapshots of brain activity. We looked at data from before the period of DBS. Then they had 6 months of DBS, during which the patients in this cohort all got better, or at least had a 50% improvement on the HDRS, which is an important clinical scale. And then we were able to, again, look at the data from after the 6 month period of DBS. And we had usable data from 8 patients in total who showed a good clinical response. So first of all, you might already be thinking, we're not looking during the deep brain stimulation, which is an important caveat. This system wasn't able to get high quality data during active stimulation because it's basically electrical stimulation at 130 hertz and it's recording from electrodes that are right next to the stimulation electrodes. So we tried to have a look at that data, but we couldn't really filter out anything useful. So we're looking at before and after. Also, we can quantify the changes between before and after, but because the study wasn't set up to look at the causality, this is going to be a correlational study only. So what can we look at? So one of the most distinctive features of sleep in the brain is slow wave activity. So if we talk about deep sleep, we talk about non-REM sleep. And this is important for things such as memory consolidation, but also for various metabolic housekeeping processes. So so two really important functions of sleep. And they are the kind of big slow wave that I showed you earlier in that picture. We can also look at sleep spindles. These are higher frequency, brief oscillations. They occur during, in particular, some of the lighter stages of non-REM sleep, and they seem to have important memory functions in particular. And then finally, we can look at sleep structure. So during sleep, the brain undergoes these cycles of non-REM sleep and REM sleep that sort of alternate. You might get 3, 4 per night. And generally, in healthy people, we tend to hit our deepest sleep in the early parts of the night. And then as you get later in the night, you get lighter and lighter non-REM sleep, and you get more REM, more longer periods of REM sleep. So what do we see in the patients? So first of all, this is kind of the data we get. We get local field potential data, which is essentially like EEG, except the electrodes are deep inside the brain rather than on the scalp, because this was from the actual deep brain stimulation target. And what we can do, first of all, is just look at the strength of the oscillations of the brain waves in these low frequencies associated with non-REM sleep. And if we do that, in this particular case, you can see that here there's high slow wave power in the early hours of the night, and as you get sort of later and later, or later in the day, you get these more high frequency, more flatlining activities. When we looked at the timing of this activity, we tried to use the timing of this activity to infer sleep structure. So this is an example of a patient before deep brain stimulation. And in this snapshot of one day, I don't think this pointer is quite bright enough. You can see that here they hit a period of quite deep sleep at around sort of 3, 4 a.m. And if you look at their activity on a 24-hour clock face over there, what you can see is that across this multi-day period, they seem to hit their deepest sleep at about 4. If we look at the same patient after deep brain stimulation, you can see here in the example that there is some slow wave activity at midnight. But really, the fit through all their data points shows that they hit their peak slow wave activity at around 11 in this case. This is obviously a single patient, but across the 8 patients, here's the average profile. So in orange is after DBS and in blue is before DBS. And if you look at the peak time between these patients, you can see that virtually all patients, and especially those with very late slow wave peaks, seem to have shifted towards an earlier time of night. So this is very interesting and consistent with this idea that people with depression have this sleep structure that is organized with deeper sleep sort of delayed into the night, and it seems to shift back as they get better. Another thing we looked at was the sleep spindle activity. And so one problem is that we had a very sparse data set, and we had data from a structure where normally people do not record neural activity in humans, because normally we don't just implant electrodes for research purposes. So we tried to use a validated an algorithm that was used for a large data study across many EEG recordings, I think about 11,000. And we tried to see if we could use the same approach to detect spindles in the local field potentials, because we weren't necessarily sure what sort of visual features we should look for. And when we did this, it extracted a few of these episodes of spindle-like activity. But what was reassuring is that if we looked at when slow wave power was high in a particular patient, and when the algorithm actually picked up high spindle activity, these two were very much aligned in the same kind of time periods. If we looked at how often spindles occurred, there was an increase in basically every single patient in terms of the occurrence of sleep spindles, which is generally considered to be a good thing. And what's also kind of reassuring to see is that just like the slow wave activity, the spindle activity seemed to shift towards earlier in the night. So what can we conclude from this? First of all, the earlier slow wave activity at night, is it that patients go to bed earlier? Are they basically showing evidence of becoming a slightly earlier chronotype? Is it the case that they go to bed at the same time but have healthier sleep structure, so more like basically non-depressed volunteers? So one thing to note is that actually the participants themselves didn't report any strong changes in their sleep quality. So by which we can maybe assume that they might have spent the same amount of time in bed, they might have spent the same amount of time awake. So that might be a vote for the idea of the sleep structure being different. The fact that there were more sleep spindles is encouraging. That they're generally positively correlated with a number of cognitive functions, and in, for instance, the aging brain, the sleep spindle activity goes down. In terms of implications, I would say this is indirect evidence that deep brain stimulation could have long-term effects on sleep microstructures, so these specific brain waves, as well as the macrostructure, so the sleep cycles across the night. However, in terms of interpreting this, is this correlation or causality? We capitalized on a data set that was shared with us, but the study was not set up to specifically look into sleep. And so we can't say this for certain, and we lack ground truth. So we didn't have an objective sleep measure from these patients. And so really the most important thing that I would say based on this study really is that is key to start explicitly monitoring sleep across clinical trials for deep brain stimulation using techniques such as EEG and polysomnography, which are the kind of gold standard. But also, you can incorporate things like wearables. Even a Fitbit gives, pretty decent data, at least on when someone's actually resting in bed, even if it doesn't give fine-grained data on sleep structure. And even just self-report sleep diaries, how did you sleep on a night-by-night basis, can be really informative. Another thing is that a future deep brain stimulation system might actually try and optimize this sort of effect. So can we work towards actually aligning and targeting sleep and circadian rhythms? And that is the final part of my talk, where I'll talk a little bit about the Dynamo deep brain stimulation system. So if we want to turn deep brain stimulation systems into good regulators of physiology, what do we need? So the current systems already start incorporating some sensor data to find biomarkers or evidence of symptoms. But we might also want to start thinking like our own circadian physiology and incorporate, for instance, the clock, some sense of time of day into this system. And in cases where circadian rhythms are disrupted, we might actually say, we're going to be prescriptive and we're going to set a clock on the device that might help keep you in line with the day and night where you are. And then this all needs to be incorporated into some kind of model that also has an idea of what the stimulation that it provides is going to due to physiology. And this really would get you into a physiology-inspired kind of zone where you create a system that will really interact with that physiology in an integrated manner. So what we want to do is we want to respond to behavior and brain activity changes, just like current closed-loop systems do, but also predict circadian changes in patient needs. So anticipate biomarker patterns, but also things like sleep or wake. And finally, we might prescribe a therapy schedule for patients in which sleep or circadian rhythms have become dysfunctional. And some work towards that we've done with our industry partner. So this is the PicoStim device by Bioinduction, and they have, we've got a partnership with them, allowing us to develop essentially an algorithm toolbox as firmware to enable various aspects of functionality of this system. And we've got a number of clinical trials running with this system now. So it incorporates an amplifier for brain signal, so we can record from the system. It's got an accelerometer that can be used to trigger changes in therapy. And I guess also relevant is that it's got wireless communication, and it's got a rechargeable battery. This is actually quite, it seems very trivial, but it's a very important thing in the DBS space, because a lot of the times research participants in deep brain stimulation studies that activate more advanced features of their systems are reducing their system lifetime if they don't have a rechargeable battery. And so having the rechargeable battery really opens up a lot more, well, we can do research without negatively affecting the standard of care for the patient. There's a patient controller that can interact with the system and change therapy settings, as well as the clinician software that can set the overarching sort of therapy plan. And then there's ways to, there's an API basically that allows us to do all sorts of interesting data science on the data that is gathered from the system. And we can then, use that to change the therapy parameters. This is the system in situ. So as you can see, it's a cranially mounted system, which has some good advantages. First of all, by being away from the heart, it actually has a cleaner signal, because the heart, the electrocardiographic signal is actually a big source of artifact in some of the closed-loop devices that are typically implanted in the chest. And secondly, because the leads don't need to sort of go through the neck, it's more suitable also for children who still need to grow. So I'll very briefly talk about two trials. So the first trial is on multiple systems atrophy. This is a neurodegenerative disease that has some similar features to Parkinson's. However, it has a very strong involvement of the autonomic nervous system. So it leads to strong blood pressure fluctuations, heart rate fluctuations, changes in alertness, digestive symptoms. So it's, the whole system basically goes a bit haywire. And it gives people very poor sleep at night, as well as excessive daytime sleepiness as well. And so to target this, we target the pedunculopontine nucleus, which is a hub in basically regulating our alertness levels, activating the autonomic nervous system. And what we do is, using a scheduler, you're using a clock-based scheduler, we actually set a sleep time for the patient where we change the stimulation pattern in order to favor sleep. Because if we stimulate the autonomic nervous system at a high level at all times, it's essentially keeping people awake. So instead, there's two nighttime modes that are designed to allow for deeper and less deep sleep, that contrast with the kind of continuous stimulation that people would get these days. And just a very quick, so we've only got a few cases in this trial, so I can only give you a case study here. But looking at the scheduled versus the continuous settings, people spend less time awake, or the patients spend less time awake after sleep onset. Their REM sleep wasn't affected. They got a lot more slow wave sleep, and they spent less time in the lighter stages of slow wave sleep. So this broadly indicates that basically brain stimulation of these targets has the potential to affect sleep, and that something like scheduled therapy settings might help people gain sleep while giving them good daytime therapy. A second trial that we're working on is a trial of deep brain stimulation of the central median thalamus in a pediatric population with Lennox-Gastaut syndrome. The reason that we're doing a trial with Great Ormond Street in a pediatric population is the fact that in this particular syndrome, with a very high seizure burden, patients, well, first of all, have a very poor prognosis, but often end up with lack of independence, with learning disabilities. And these are not inherent to the syndrome. They're secondary to the large seizure burden that there is. So if you would do a clinical trial to try and help patients at age 18, you might reduce their seizure burden, you might increase their quality of life, but they've already had a long developmental seizure burden. That means that they probably will never really catch up on a lot of development. So the idea is that if you can get there earlier, you might give people a better chance of catching up. The device we use is more optimal for children than some of the existing devices. So I already said it's got a cranial mount, it's rechargeable. The firmware can be wirelessly updated to allow for more advanced therapies to be delivered to them. So it should be a relatively child-friendly device compared to some of the other systems that are out there. And this is a collaboration with Great Ormond Street Hospital as well as UCL and King's College. So the target is actually, if you look at fundamental neuroscience, so it's currently already clinically applied as a target for controlling epileptic seizures. But if you look at some fundamental neuroscience research, central median thalamus is implicated in orchestrating some of these sleep activities in the brain. And so, we may well be doing something to sleep. And, if we're fixing enough seizures, it might balance out for the patient, but it would nevertheless be very important to characterize what is going on in response to stimulation. And secondly, in epilepsy, there are often very strong circadian patterns in seizures. So this is just an example of the seizure diary of one of the patients in this trial. And what you can see, so here you see a number of days, and here you see basically the 24 hours of the day. And as you can see, these types of seizures almost exclusively occur between the hours of about 6, 7 in the morning. They don't occur between about 7 in the morning and 9 in the evening. And then there are whole clusters of them. And so really an optimal system might actually try to start exploiting these sort of predictable patterns. So in sum, I hope to have convinced you that sleep and circadian rhythms should really be factored into deep brain stimulation design as well as into deep brain stimulation clinical trials. I've given you a case study of deep brain stimulation for depression, where we saw shifts in people's sleep patterns as well as shifts in certain types of sleep activities following deep brain stimulation. And finally, I've given you a brief overview of some work that we're doing, trying to develop a system that is respecting and is aware of sleep and circadian rhythms, and giving you a flavor of some of the trials and their relevance there. And so vision for the future is to go from these open loop continuous approaches and sort of move even beyond closed loop to this idea of truly integrating with our physiology, making a system that can be prescriptive, reactive, predictive, based on an internal model of physiology.
Thank you so much, Joram. Now we'll open the floor for a couple of questions. Yes, please.
Thank you. Great talk. What's the lifespan for these implants? How long can they stay in the patients? What kind of things affect it, and how could you maybe make them last longer?
That's a very good point. So I'm not 100% sure on the official lifespan of the PicoStim device. There are. I think basically a lot of all the devices are engineered for people with Parkinson's disease who are in their 60s, 70s, and so initially the lifespan of devices, 5 to 10 years was acceptable. The rechargeable device, I don't know at what point they're doing a lot of work on trying to make the battery be sort of not sort of lose its charge as time goes on. I don't know exactly what the official lifetime of the device is. Sorry. The battery is one of the biggest considerations, though, because it's just going through the recharge cycles. So having battery materials that can support that is, I think, one of the biggest challenges.
Oh, so when your studies have involved maybe 8 or 9 folks sometimes, because it's difficult.
Yeah.
Have you considered factors like extreme sleep apnea? Because I've known of people who've had that and their circadian rhythms get really screwed up. And what I'm wondering is, if you were doing a study of something in a disease X, have you had to go and consider or notice some effects of people who might have that kind of a problem in terms of getting sleep? Or
so, this is exactly what I'm trying to advocate for. The data analysis projects that we've done so far, we didn't have that data on the patients because we worked with a data set from an external group. We're trying to collect more sleep data on our patients in the trials that we have control over. And so we haven't specifically thought about sleep apnea. We're giving sleep questionnaires, but this is, especially in elderly populations, it's going to be an important factor. Yeah. I'll be mindful of that.
Thank you so much. More questions? I'll go here and then I'll come back to you. Thank you.
Yeah, thank you for the talk. I wanted to ask, given the importance of, for example, hippocampal replay and the coordination of all these ripples with the slow wave, oscillations, have you considered maybe providing for future studies, say, memory tasks, right? Because this is important for memory consolidation, and maybe see how even, like, as the data analysis that you conducted had indicated, like, there is no amelioration of how they feel, but maybe they are performing better cognitively, things like memory. Have you considered that?
So the sleep spindles the increase in sleep spindles, we would hope to correlate with something like improvement in cognitive performance. We are not currently doing cognitive specific memory task with the patient cohorts that we have, just because we don't want to overburden the kind of clinical trials. But those would be really interesting follow-ups. I do also work with Andrew Sharrett at the MRC Brain Network Dynamics Unit, where we're working with some animal models, and that's not me personally, but others are actually working on, for instance, amplifying hippocampal ripples and doing memory tasks. And obviously, when you're doing animal work, there is a bit more freedom to explore a larger variable space and get more data. When we work with patients, we always have to really think about balancing the burden and so especially the first clinical trials are, in terms of the outcome measures, are very geared towards what we really need to know, and then follow-ups once they have the systems and are on their regular care. Yeah, we can try and explore those sorts of questions.
Hello. Hey, yeah, super cool talk. I never thought about the role of sleep in DBS programming, so very fascinating. I might have missed it, but how are you using like sleep to change either like the biomarker detection or the stimulation programming to kind of target all those seizures that you're seeing pop up at night?
Okay, so this, so at the moment we're not doing that yet in the trial. So in the trial multiple systems atrophy, we're just using an onboard clock to essentially prescribe a circadian rhythm, or we kind of assume that there's a sleep time for the patient. For the epilepsy trial at the moment is just a continuous stimulation, and we're monitoring sleep. But I was just highlighting that the kind of sleep and circadian relevance that future systems might want to exploit. And so the system is instrumented to look at neural activity. And so in the future, yeah, there are things that we might want to explore there. But at the moment, it's just continuous therapy.